I will explain about the system 1 for the calculation part. So first, the system 1, the transfer function that the equation gives is k over s 0.2 s plus 3 and s plus 4. So first, we need to for the system 1, we need to determine is it the open loop pulse and the 0 for the system. For the transfer function that we get, it is the open loop and there is no 0 and there is a 3 poles that is -4, -3 and 0.2. Then we need to find the breakaway point or breaking point. So by using the characteristic equation, we substitute the transfer function into the characteristic equation to find the value of k for the system. So that we get k equals to -s power of 3 minus 6.8 s power square minus 10.6 s plus 2.4. Then we differentiate the value of k to find the s1 and s2. So the s1 is -1 and s2 is -3.53. So value s1 is closer to the origin than s2. So the breakaway point is at s1 equals to -1. Then we need to find the j omega axis crossing point by using the characteristic equation and use the table. From the s1 we get k equals to 74.48, and using the s2 row with k equals to 74.48, the value of s is plus minus 3.26 j. Then draw the root locus on the graph paper. So first we need to determine the number of branches by using the formula number of branches equals to number of poles minus number of 0. So 3 minus 0 get the branch equals to 3. After that, using the formula of asymptotic crossing point, we get -2.3, and asymptotic angle, we get k equals to 0, 1, 2. When k equals to 0, the angle is 60. When k equals to 1, we got 180, and when k equals to 2, we get 300. So this is our graph. Then we need to find the range of the value of k for overdamped, vertically damped, undamped, and undamped. So first we do the overdamped first. When the system is vertically damped, the poles are at s equals to -1. Using our magnetic collision formula, k equals to pole length over 0 length, poles at 94, 93, and 0.2, then we get 7.2. For the range value of k for overdamped, 7.2, less than k, less than 74.4. For vertically damped, k equals to 7.2, and then if k is greater than 74.48, and then 0 less than k less than 7.2. So that's all for the calculation part for system 1.
Hi, Assalamualaikum and good day everyone. So now I will presenting my part for this control system engineering assignment. So I will be explaining about how to design a PID controller so that the new peak time is 2/3 of the original peak time with 20% overshoot and 0 steady state error. So this is for the system 1. So first of all, we write the design criteria here, and then we use this formula with the given damping, with the given overshoot to get the damping ratio. After that, we calculate the angle here. Why? Because we want to know the we want to know the desired location for that damping ratio. So we get this value, and then from there we use this formula. Hmm, from that we use this pole location formula to calculate the value of this omega n, and then from there we can calculate the peak time at that pole location. So after we obtain the original peak time, we can compare it with the new peak time, and then from there we just reverse the order to calculate the omega n. Why? Because we want to know the location. We want to know the location to obtain the new peak time. And then after we know the location of the new desired pole location to obtain the new peak time, uh, okay. After we know after we know the new location for the new peak time, we have to know whether our original road locus go through that location or not. So usually it doesn't. That is the reason why we use PID. So we use PID to change the trajectory of the root locus. So that's why we do PID lah kan. Lepas tu uh, okay. So the procedure of PID is first we do PD. So PD requires us to put a 0 at a location where it will change the trajectory of the original root locus, so that it can go to this point. So I substitute that 0 with A here. So we need to know the value of A, which is the 0. So we use the formula of angle of departure here, and then we get the value of A. So location of A will be at negative 4.75. And now we have to know, after we have put this 0, we have to know the value of gain K in order to obtain that desired pole location. So we use this formula of product of pole length divided by product of zero length. The product of pole length formula means that the product of each pole length from the desired pole location. So we use that formula and then get this value of gain K. So now we put everything we have obtained here into the equation of PD, which is K bracket S plus A. So K means the gain needed to be adjusted to obtain the desired pole location, and A is the location of the new 0. So we only success do the PD part, and now we have to, well, this is actually PI. So adding the PI part, so the equation of PI part is actually just S plus K, S plus B over S. So the procedure of doing PI part is first we put a 0 closest to 0, but closest to the origin, but not at the origin. So I let that value of P equal to 0.1, and then we put a pole at origin. Why? Because I will explain it later. So we do everything here, and then we get this PID equation. So from from there we just cascade the whole system. So I just multiply the original transfer function with the PID transfer function, so we get this. So this is the overall transfer function equation. So now the design requirement asks us to make it have no steady state error, zero steady state error, right? So in order to do that, we need to compare this. We need to know the system type for this overall equation. How? We need to look at the number of poles at the origin, which is here as here is only s power of 1, so which means it has only one pole at the origin, so it is system type 1. So this is the reason why we do the ID part, because we want to compare it with this table. So from this table, we know that system a system type 1, when being supplied with a unit step input, it will give us a zero steady state error. So the design requirement is met. So here is for system 2 again. First of all, we write the design criteria, and then we calculate the value of damping ratio zeta, which is the same for all three systems. So the angle will also be the same. So we draw that angle. We do draw that damping ratio with that angle here on our locus. So we get the desired pole location. So from that desired pole location, we must calculate the value of omega n to obtain that pole location. Why? Because we want to know the value of peak time, the original peak time, and then after we obtain the value of original peak time, we compare it with the new peak time to get this, and then now we know the full design requirement here, and then from there we must know the value of new omega n. Because we want to know the new desired pole location to make this design criteria here. So we get this pole location. So we know that from our original locus, the trajectory does not go through this point, so that's why we do PD part. So we do PD. In order to do PD, we need to know the location of the zero needed to be at in our original locus. So we let it with A here as our 0. So we use the formula of angle of departure here to obtain this value. So we get so here are the calculation part. We only use the basic we only use the basic theorem. We only use the basic theorem Pythagoras formula to obtain that zero location. So we get our zero location at negative 1.34, and now we need to know after we know the location of zero, we need to know the value of gain k needed to be adjusted to obtain that pole location. So we use the formula of product of pole length from the desired pole location divided by product of zero length from the pole location. So we only use theorem Pythagoras here, and then we get our value of gain k needed to be adjusted is 5.31. So after we get this value of gain k, we sub everything into the equation of PD. Equation of PD, which is k bracket s plus a. So we know k equals 5.31, a equals 1.34. We sub this value into the equation, so we get this equation. And then again, this is a mistake. It's actually adding a pi part. So pi part only consists of k s plus b over s. So again, b is the location of 0 needed to be located closest to the origin, but not exactly at the origin. So we let it with 0.1, and then we must put pole at the origin. Why? Because we want to cancel out the effect of the pole, because every time we put an additional 0 or pole into the locus, will change the behavior of the system response. It will change the behavior of the system response. In order to avoid that from happening, we need to put a counter effect to it. For example, if we put zero, additional zero, we must put a pole, additional pole, closest to the value but not exactly at the value. That is the reason why we do PI part. Again, we also do PI part in order to compare the general equation with this table. So we again cascade the whole system transfer function, we get this general equation. So we know from this equation the overall system is a type 1 system. Again, a type 1 system will have zero steady state error if being supplied with a unit step input. So the design requirement is met for all three design requirements. Okay, now here for the system 3. Again, here is the design requirement needed to be met, and then so from this design requirement, we first must know the value of damping ratio needed, and then we must know the angle of the damping ratio, and then after we obtain that, we draw the line of the damping ratio out to our root locus. We must locate our desired pole location, which is we get this value, and then from here we must know the value of omega n in order to obtain this desired pole location, and from there we can know our peak time, our original peak time, and then we can compare it to obtain a new peak time, and then from there we must know the value of our new omega n. From there we can know the new desired pole location to meet the design requirement. So again, this pole does not, our original root locus trajectory does not go through this pole, so we must do PD part. So first in PD we must know the value of the zero needed to be added. So we use this angle of departure equation again on just a basic theorem Pythagoras. So from there we know that the location of a new zero needed to be at is at negative 1.59, and next we must know the value of gain needed to be adjusted to obtain that desired pole location. Again, just a normal theorem Pythagoras formula. We know that the value of gain k is 0.516. Now we sub in all these values into the PD equation. So we get this B. So now again this is Pi. So adding Pi part, which is K S plus B over S. So B is the location of zero needed to be at closest to the origin but not at the origin. So we put it at negative 0.1, and then we put a pole at exactly at the origin. So that's basically it for Pi. So the overall equation for system transfer function is we cascade everything, so we get this. So from here we must compare it with this steady state error table. So we know that we have two pole at the origin, which means that this system is a type 2 system. So with a type 2 system, we know that if we supply a RAM input, the system steady state error will equal to 0.
Okay, this is for system number 1. So the rush time for system number 1 is 3.4, the settling time is 6.06, and then the execute is 1.5. So the value for the overtime is between 7.2 and 74.48. So the value next for the critically damp is 7.2, and then for undamp is larger than 74 74.48, And then lastly, the value for the under depth is between 0 and 7.2. Okay, this is for system number 1. So the rush time for system number 1 is 3.4, the settling time is 6.06, and then the execute is 1.5. So the value for the overtime is between 7.2 and 74.48. So the value next for the critically damp is 7.2, and then for undamped is larger than 74.48, and then lastly the value for the underdamped is between 0 and 7.2.
So part I, draw the bond plot, bond and phase diagram for system 1 on the semi-log graph paper for k equal to 5. So system 1. So system 1 we change k equal to 5. Here the calculation we use j omega. This calculation until we can get this, and then we separate, we can get the 4 equation. So this one is a magnitude for 6.375 and phase is negative 180. So the second one, P equal 0.2. So magnitude, we can see the drop until negative 40, and phase 0.02 here we can see the up. And for the third one, P equal 3. So this for the magnitude, and this one is a phase. And the last one is a P equal to 4. So this one is a magnitude for P equal 4, and this one is a phase diagram. So here the bond plot for magnitude graph when all the system factor. So we combine the all, so here we get the all for magnitude graph for system 1 only. Here for magnitude in graph for system 1, here a plot from phase diagram when all phase factor, all system factor. So this one we combine 4, so we can get here this one, here the bond plot only for system 1. Determine the gain margin and phase margin at system 1. Gain margin is the gain where the frequency at phase negative 180. In this case, it is at phase 6.38 at 0 radians, and phase negative 33.6 at 3.28 radians. Phase diagram, phase margin is the phase where the frequency at magnitude 0 dB. In this case, phase equal 49. Design the next part is design the lag compensator for system 1 to yield at tenfold improvement in steady state error over the gain compensated system while keeping the damping ratio equals 0.2. So only for the system 1. So damping ratio 0.2. Design phase margin equal theta. So this one the formula, include the formula. So we get 22.6 from the bond plot. The value of the design phase margin frequency is about 0.1 radian and 2 radians. So after we plus the final answer here, we get 157.4. Look the first plot where the phase is negative 57.4. So this one is a graph. So as we can see, the drop here. So this one is from the magnitude graph. When frequency 0.1, radius magnitude 6.375 dB. When frequency second 2 radians, magnitude negative 16.5 dB. So using formula, this one is formula. When magnitude 6.375 dB, K equal 2.4. When magnitude equal negative 16.5 dB, K equal 33.417. So this one is a table, damping type, under dam, vertical dam, over dam, under dam, damping ratio. So in this one is a ratio. Since the requested damping ratio equal 0.2, the system is under dam case. The value of gain K should be in range from 7.2 to 74.48. So refer answer I4. So the value of gain K to assume the damping ratio 0.2 is K 33.417. So we can see the graph here. And this one graph or formula of K. Kp is this one is a formula. We insert the formula, then we get 13.92. So we use all the formula to get the answer. And then therefore the new transfer function that yield is therefore improved in the steady state error. So they improve the steady state error. So here the graph. Desired damping ratio equals 0.2. So this one is a formula again. The phase margin need to be increased by 30 degree and the desired phase margin become 32.6 degree. From the above plot, the value of the desired phase margin frequency is about 0.18 radians and 1.6 radians. So look at the phase plot where the phase is negative 157.4 for the magnitude graph, where the frequency equal 1.6 radians, magnitude equals 15.4 dB, neglect the other magnitude and frequency equal 0.16 radians. Okay, the light composer must provide negative 50.4 dB at attenuation at 1.6 radian. So here you can see the negative 1.4 dB, 15.4 dB. Here it dropped. And then it is a frequency. The using the formula again, we how to get the answer on the graph again. So using the formula, same formula, include and then separate all of them, so we can get phi. So we can get phi the graph. So this one, the first one, magnitude and phase for 71.19. So the magnitude and phase. So this one, if P equals 0.002, this one is magnitude and phase diagram. Same, all we use the same one. So until the last one. Okay, So you can get Z equal 0.018. So this one the graph like this. Okay, so we combine the all the graph. So here we get the all. We get all like this. We combine all. So this one so we separate. So this one the first one like this graph, and then like this, and this one for the software in MATLAB system 1 we get like this. So frequency we get 0.0138, magnitude at 6.35 dB. So gain margin we get 23.5, frequency we get 3.28, closed loop stable, yes, rest. So delay margin, phase margin we get 49 degree, delay margin we get 2.37, frequency radian we get 0.36, closed loop stable. What plot one phase diagram when K is equal to 5. So this one we change the for I. So K equal to 5. So we can get peak gain negative 23.1, frequency 0.37, gain margin 41.8, frequency we get 4.1, closed loop. Frequency radian we get 0.37, phase we get per 7 negative 7 6.1. So frequency radian we get as 5.02, phase degree we get negative 193. So this one plot phase diagram when like composite. So for the system 2, here we got plot and phase diagram. So this one plot, we can get frequency, we get the 0.637, and magnitude we get 3.663, and the frequency we get the phase margin at 1.6, delay margin we get 1.44, frequency radian we get 0.989 for frequency. So the next one, system 3, plot. Here plot gain margin we get a 9.94, frequency 0.606, peak gain we negative 6.22, frequency 2.31, gain margin 43.2, frequency radian 5.71 for frequency radian 0.103, phase degree we get a 318. So and then he drop a frequency 0.764, phase degree 156. So that's all.
Next, we move on to calculation part for system 2. First, the transfer function that we get is K s squared plus 20 over s minus 0.5 s squared plus 10s plus 25. So first we need to determine either it open loop or closed loop, and is it F0 or not for the system. So in the transfer function that we get, you can say that this is the open loop post and there is 0 for the system. So for the 0, we get S1 J 4.47, S2 negative J 4.47. For pole, we get S1 equals to negative 5, S2 we get negative 5. So there is 3 poles and 2 0. Next, for breakaway point and breaking point. So same by using the characteristic equation 1 plus 2g s h s equals to 0. We substitute that the equation transfer function into the characteristic equation to find the value of k. Then we differentiate to k, we get s4 plus 40s plus 405s plus 400 equals to 0. So for the s1 equals to negative 1.11, s2 negative 5, s3 equals to 3.50 plus j 7.10, s4 equals to 3.05 minus j 7.90. So the value s1 is closest to origin, so the breakaway is at s1 equals to negative 1.11. Next, for the j omega axis crossing point, the characteristic equation s3 s cubed plus 9.5 s squared plus 20s minus 12.5 plus k s squared plus 20 equals to 0. By using the table from s1, we got negative 12.5 plus 90 plus 20k minus 20k equals to 0. K will be eliminated in this calculation because there are no given value. K to bring the root locus to the imaginary axis. The root locus will only pass to imaginary axis at plus minus j 4.47 as there are 0 located there. However, the poles will not cross the imaginary axis. So next we draw the root locus on the graph paper. So this is our root locus from our calculation. And then we find the range of value gain k for overdamped, critically damped, undamped, and underdamped. So first we do the when the system is critically damped, the poles are at s equals to negative 1.11. Using the magnetic condition formula, k equals to pole length over 0 length, we get the poles negative 5, negative 5, and 0.5. Meanwhile, for the 0, negative j 4.47 and j 4.47, we get 1.148. For the overdamp, we get 1.148 less than k. For critically damped, k equals to 1.148. Undamped, no undamped case at the root locus because it will not go through the imaginary axis. And last underdamped, got 0 less than k less than 1.148. And that's all. Thank you.
So this is the system for number 2. The rise time is 5.12 and then the setting time is 9.39. And then the value for amplitude is 2.66. So the value for over them is between 1.148 and then the infinity. So the critically damped for the value critically damped is 1.48. So this is no other than no value for the other than because it does not go through for the imaginary axis. And lastly, the value for the under them is between 0 until 1.148.
And now, last but not least, our calculation part for system 3. So the transformation that we get is gs equals to k bracket s square minus 5s plus 2 over s bracket s square plus 5 s square plus 5s plus 6. So first we need to determine if it's open loop and it is as zero system. So the system is open loop and there are zero to the system. So the zero is S1 equals to 4.56, S2 is 0.44. Meanwhile, for the post, we get S1 is 2.24 and S2 is 2.24. So there are G0 is 4.56 and 0.44. Poles, there are 4, there is 0, that is G2.24, G2.24, that is 2 and that is 3. Then we find the break point or breaking point by using the same formula, same equation, characteristic equation, 1 plus 2gs hs equals to 0. We substitute that to transfer function that we get to find the value of k and see this is shape like okay. Then we get 3s6 minus 10s5 minus 54s4 minus 78s2 minus 89s2 plus 100s plus 16 equals to 0. As the polynomial is a degree higher than 4, as 4 perfect polynomial, we cannot solve the equation to find the point manually. So we use the magnet function to find the possible rate for the breakpoints. So from the value obtained from MATLAB, the breakpoint is at s equals to -0.4587 and 0.8671. These values are the closest to the origin than other value. So K omega x is closing point. Using the table, the characteristic equation is S5 plus 5 S4 plus 11 S3 plus 25 plus K S square plus 30 plus K S plus 2K is 0. So for the S1, we get K1 equals to 0, K2 equals to 5.769 and K3 equals to 170.26. So using the S2 row with K1 equals to 0, K2 equals to 5.796, K3 equals to 170.26. When K equals to 0, S equals to 0. When K equals to 5.769, S equals to plus minus 0.621. And lastly, when K equals to 170.26, S equals to plus minus 5.93. Then we need to draw the root locus of the graph. So first we need to determine the number of times. Number of pole minus number of zero. The number of branch equals 3. Then we find the asymptotic point is 23.22 plus for the asymptotic angle when K equals to 0. The angle is 60 and K equals to 1 and K is 102. And when K equals to 2, the angle is 300. So this is the graph of our vectors. And last, we need to find the range of value of K for overlap, critically damp, undamp, and underdamped. So when the system is critically damped, the poles are at S equals to 0.4587. Using our magnitude condition formula, K equals to pole length over zero length. Poles equals to 0, negative J2.4, J2.4, negative 2, and negative 3. So the range value of K that we got for overlap 0 less than K less than 2.00 and K greater than k equals to 2.07, and then k less than 5.7146, and again 2.0785 less than k less than 5.7146, and that's all the completion for this system.
Okay, Assalamualaikum. So this is for system number 3. So the rise time is 7.46. The amplitude is 1, and the settling time is 15.9. So how to find the overtime? So the value for overtime is between 0 and 2.079, and then for the critically damped is k equal to 2.079, and then for the under dam is between 2.079 and 5.7146, and lastly for undam is k is larger than 5.7146. Okay, Assalamualaikum. My name is Muhammad Afiq Izzuddin. So now I will continue for my part by explaining how we get the root locus and then the value and the step response. So this is for the system 1. So at the left side is the root locus for the system 1, and then the right side is the step response. So we can see the rise time is 7.49, and then the settling time is 13.8. So we can see here no overshoot, and then the peak deviation is 1.92. So then we move to the PID controller. So this is the step response after we do the PID controller. So we can see here the overshoot is 16.4, and then the rise time is 0.595. So and then we can find the KP, KI, and KD. So the value is here. So for the KP is 24.57, and then for KI is 4.46, and lastly for KD is 11.68. Next we move for the step response after we do the lag compensator. So this is the value that we get. So after the lag compensator, the rise time we get is 2.5. The settling time is 51.2, and then the overshoot is 69.6. So we move to the system 2. So as we can see, for the left side is the root locus for the system 2, and the right side is the response for the system 2. So we can see here the rise time for the system 2 is 4.74, the settling time is 8.61, then no overshoot. So this is the step response for system 2 after PID controller. We can see here the overshoot is 32, rise time is 0.752, and then so on. So the KP, KI, KD, the value we get is KP is 3.31, the KI is 0.11, and lastly for KD is 0.90. So we move to the system 3. So this is the root locus for system 3, and then this the response for the system 3. So this is for the step response with PID controller from system 3, and then the value for the KP, KI, and KD is here. For value for KP is 0.07, so for KI is 0, and lastly for KD is 1.00. So that's all from me for root locus.
So now I will be moving to discussion. So this is the discussion for root locus. So for system 1, the root locus and step response indicate a faster response with significant overshoot in the uncompensated system. With the PID controller, there is an improvement in rush time and reduction in overshoot, making the system more responsive and stable. The uncompensated system shows a steady state error which is corrected by the PID controller, ensuring zero steady state error with more stable output. For system 2, the system exhibits a slower transient response initially with considerable overshoot and oscillations. The introduction of the PID controller improves the system's damping and reduces overshoot, enhancing the transient stability. Without compensation, there is a noticeable steady-state error. The PID controller effectively eliminates this error, providing precise steady-state performance. For system 3, it shows an underdamped response with oscillations in the uncompensated state. The PID controller application significantly reduces the overshoot and oscillatory behavior, leading to a more stable transient response. The uncompensated system has a higher steady-state error. With the PID controller, the steady-state error approaches zero, improving accuracy. So, to compare the values obtained in simulation and calculations, the simulations closely match the theoretical calculations for all three systems, confirming the accuracy of the root locus and stability analysis. Small discrepancies may exist due to numerical approximations or rounding in manual calculations. The gain values for stability margins and damping ratios obtained in simulations align with the calculated values. The simulation results provide a practical validation of the theoretical approach. Now, we can choose the best performance between all three systems. System 1 offers the best balance between transient response and steady-state accuracy after compensation, making it the most stable and responsive system. While System 2 demonstrates improved stability and reduced overshoot after compensation, but is slower in response compared to System 1. Whereas System 3, while effective, it exhibits more oscillatory behavior than System 1, even after compensation. So the best performance goes to System 1 as the best performing system due to its superior stability, quicker settling time, and minimal steady-state error after compensation. So, to compare between compensated and uncompensated system, all three systems show significant overshoot and steady-state error. The root locus for the uncompensated system indicates less stability with poles closer to the imaginary axis. For the compensated system using PID controller, the addition of the PID controller improves both transient and steady-state performance. Compensated system shows reduced overshoot, faster settling times, and zero steady-state error, enhancing overall system stability and accuracy. So, the lag compensator in System 1 was particularly effective in improving steady-state performance without significantly affecting the transient response, highlighting the utility of compensators in fine-tuning control systems. The analysis of gain and phase margin from both plots confirms that all systems are more robust and stable after compensation. This margin provides insight into the stability buffer available before reaching instability. The compensator system maintain their type and order with improvement focused on reducing errors and improving the response time. So the analysis of System 1, 2 and 3 reveals that the compensation, particularly using PID controllers, significantly enhances system stability and performance. System 1 stands out as the most stable and responsive system post-compensation. The theoretical calculations and simulations are consistent, validating the approaches used. Overall, the implementation of compensators effectively meets the desired performance improvements in all systems. Okay, so sekarang kita akan buat plot. Now I will be providing discussion for both plot system. So the differences between calculated and simulated results. Nature of results, calculated results, derived from analytical formulas and approximations, for example, formulas for gain margin, phase margin, or compensator parameters. For instance, the gain and phase margin calculations rely on specific formulas where parameters like damping ratio and desired phase margins are inputs. For simulated results obtained using software tools or experimental setups often visualized through plots, they show how a system behaves under specific conditions and include a real-world nuances like system delays or non-linearities. Calculated results assume ideal conditions and may overlook factors like noise or external influences. Simulation incorporates more practical aspects, offering a closer approximation to a real-world performance. Simulations validate theoretical calculations. Discrepancies, such as differences in phase or magnitude at specific frequencies, highlight areas where theory and practice diverge. Uncompensated system, the response is purely determined by the open load transfer function G1S, which may exhibit inadequate steady-state performance such as higher errors and lower phase margins. Lag compensated system is designed to improve steady-state performance without significantly affecting stability. For example, a lag compensator added a tenfold improvement in steady-state error for system 1. For phase and gain margins, the addition of lag compensator shifts the board plot, typically enhancing the phase margin and reducing sensitivity to frequency variations. This is evident in the updated phase margin calculations in the documents where a desired phase margin was achieved through compensator design. Transfer function impact. The uncompensated system transfer function emphasizes raw system dynamics, whereas the compensated version introduces terms to adjust phase and gain at critical frequencies. So, the comprehensive performance analysis, steady-state error. In System 1, a lag compensator improved the steady-state gain by a factor of 10. These adjustments highlight how compensators enhance precision in systems requiring fine control. Frequency response. From the board plots, the lag compensation altered magnitude and phase plots, particularly at low frequencies where the compensator's attenuation provided stability while maintaining desirable performance. Design optimization. Adjustments in gain K or damping ratio zeta indicate an iterative design process. For instance, ensuring zeta equals to 0.2 involves balancing gain to avoid underdamping while maintaining performance. Additional observations. Practical implications. Compensator design must consider hardware limitations and real-time implementation feasibility. High computational demands or precision requirements may challenge practical use. Iterative design and verification. Each system requires iteration between calculation, simulation, and experimental validation. As observed, calculated damping ratio and phase margins were cross-referenced with both plots to finalize the designs. Finally, the phase crossover and stability. Stability conditions, for instance, phase margin greater than 22.6 degrees, were critical in determining compensator parameters, reinforcing the importance of margin calculations in control systems. So now I will be explaining about discussion and conclusion for overall assignment. So first of all, we can compare the terms of transient and steady-state response. For System 1, the transient response, the locus static response indicate a faster response with significant overshoot in the uncompensated system. With the PID controller, there is an improvement in rest time and reduction in overshoot, making the system more responsive and stable. For steady-state response, the uncompensated system shows a steady-state error which is corrected by the PID controller, ensuring zero steady-state error with a more stable output. For System 2, the system exhibits a slower transient response initially with considerable overshoot and oscillations. The introduction of the PID controller improves the system's damping and reduces overshoot, enhancing transient stability. Steady state response without compensation, there is a noticeable steady state error. The PID controller effectively eliminates this error, providing precise steady state performance. System 3 shows an underdamped response with oscillations in the uncompensated state. The PID controller application significantly reduces the overshoot and oscillatory behavior, leading to a more stable transient response. Steady state response. The uncompensated system has a higher steady state error. With the PID controller, the steady state error approaches zero, improving accuracy. Simulation versus manual calculations. The simulation closely matches the theoretical calculation for all three systems, confirming the accuracy of the root locus and stability analysis. Small discrepancies may exist due to numerical approximations or rounding in manual calculations. The gain values for stability margin and damping ratio sorted in simulations align with the calculated values. The simulation results provide a practical validation of the theoretical approach. System 1 offers the best balance between transient response and steady state accuracy after compensation, making it the most stable and responsive system. System 2 demonstrates improved stability and reduced overshoot after compensation, but is lower in response compared to System 1. System 3, while effective, it exhibits more oscillatory behavior than System 1 even after compensation. Best performance goes to System 1 as the best performing system due to its superior stability, quicker settling time, and minimal steady state error after compensation. For uncompensated system, all three systems show significant overshoot and steady state error. The root locus for the uncompensated system indicates less stability with poles closer to the imaginary axis. The addition of the PID controller improves both transient and steady state performance. Compensated system shows reduced overshoot, faster settling time, and zero steady state error, enhancing overall system stability and accuracy. The lag compensator in System 1 was particularly effective in improving steady state performance without significantly affecting the transient response, highlighting the utility of compensator in fine-tuning control system. Analysis of gain and phase margin from both plot confirms that our systems are more robust and stable after compensation. This margin provides insight into the stability buffer available before reaching instability. System type and order. The compensator system maintain their type and order and improvement focus on reducing error and improving the response time. The analysis of System 1, 2, 3 reveals that compensation, particularly using PID controller, significantly enhances the system stability and performance. System 1 stands out as the most stable and responsive system post-compensation. The theoretical calculation and simulation are consistent, validating the approaches used. Overall, the implementation of compensators effectively meet the desired performance improvement in all systems. So, the comparison of calculated and simulated results consistently demonstrates strong alignment across all systems, validating the theoretical framework and the practicality of simulation tools. Key observation include System 1. The calculation of gain margin and phase margin derived from the board plot were determined using the formula. Gain margin equals to gain at phase equals negative 180, whereas the phase margin is phase at magnitude, which is 0 dB decibel. Calculation for steady state error and damping ratio also match expected result. For simulation, the MATLAB simulations reinforce this result by showing root locus trajectories and both plot consistent with calculation. Step responses confirm improved damping and reduced overshoot after compensation. For System 2, the characteristic equation for the root locus provide insights into breakaway points and stability margin. For example, breakaway point equals to the differentiation of k, which is equals to 0. So the root locus plot validated a calculated breakaway and imaginary axis crossing point. The simulated responses confirm compensation improvement in damping and reduced overshoot. For System 3, analytical method identified complex breakaway point requiring MATLAB assistance, ensuring accuracy in predictions. The lag compensator design was validated, showing improvement in transient response and steady state accuracy. System exhibited significant performance improvement post-compensation. Our compensator system showed higher overshoot, slower settling time, and substantial steady state error due to less effective pole placement near the imaginary axis. Lag compensators focus on improving steady state error while maintaining damping formula. The formula is GC equals to 1 over alpha times S plus 1 over T over S plus 1 over alpha T. This formula controls the attenuation, and T, which is period, defines the time constant. The edit controller combine proportional, integral, and derivative control to enhance damping, reduce overshoot, and eliminate steady-state error. The formula GC equals to KP plus 1 over plus KI over S plus KD. Parameters KP, KI, and KD were tuned to balance responsiveness and stability. Each system was evaluated for transient and steady-state performance. System 1, best overall performance with balanced transient response and steady-state accuracy. Transient improvement, faster rise time, reduce overshoot, and settling time. Steady-state accuracy, achieve zero steady-state error with a tenfold improvement using a LED capacitor. System 2, improve stability but slower response to compared to System 1. The capacitor significantly reduce steady-state error but the transient response remains suboptimal. System 3 showed significant oscillatory behavior in the uncompensated system. PID compensation reduced oscillation though the system remains slower than others. Root locus analysis. The root locus diagram provided a foundation for understanding system behavior under varying gain. Key findings. System 1, the root locus trajectory allowed precise compensation design ensuring damping and stability goals were met. System 2, breakaway points and gain ranges were accurately predicted with no crossing into instability regions. System 3, the MATLAB system was crucial for solving high-order polynomials, validating compensation strategies. Stability margins, the gain and phase margin from both plots confirmed that our system became more robust post-compensation. Gain margin increased for all systems, indicating a high tolerance to gain variations before instability. Phase margin is improved, ensuring reduced sensitivity to phase lag. So, in conclusion, the comprehensive analysis for System 1, 2, and 3, both uncompensated and compensated, reveals the following key insights. The performance improvement compensation, though PID controllers and LED compensators consistently enhance the instability, reduce overshoot, and eliminate steady-state error. System 1 superiority. System 1 exhibited the best overall performance, achieving optimal transient response and steady-state accuracy. Calculation and simulation consistency. Theoretical predictions and MATLAB simulations align well, validating the robustness of both approaches. Effectiveness of compensation. LED compensators excel in steady-state error correction, while PID controllers effectively balance transient and steady-state performance. By integrating theoretical calculations and simulations, the analysis ensured robust, practical, and accurate system designs. The methodologies and insights gained can guide future control system design for similar applications. That's all from us. Thank you.